So I actually feel I should explain slightly better one thing that in the last lecture I was very quick, and I don't think I gave you a good feeling for it. Okay, so at a certain point after studying certain partial differential equations, we said one way of constructing bad solutions is the following. So we were looking at something like the differential of u is, for instance, contained in a certain set K, and we wanted to start it from some relaxation of this problem, in which the relaxation is related to a sort of convex hull of the set K, where, however, the convex hull is only along some, or the hull is only constructed by taking segments along some special directions, right? So because depending on the partial differential equation that you're looking at, you might not be able to use all directions that you have in the space of gradients, right? So, and then I said there are actually situations, and these are like the most surprising situations, in which you take, for instance, a finite set of points. Between these finite set of points, there's no line which is connecting them, which lies in what I call lambda, which is kind of the cones of admissible directions. And nonetheless, this notion of convex hull gives you a set, a convex hull, a lambda convex hull with non-empty interior. Okay, so a famous example actually is given in the literature by the so-called Tartar square. Okay, and it's very elementary to explain. I should have actually explained that directly. So let's say we take as lambda, so we are in R2, so lambda is going to be like only consisting of two lines, so lambda 0 and 0 lambda, so only vertical and horizontal lines are admitted, right? So so this means if I want to define some notion of convex hull, you give me 2 points. If the segment connecting the 2 points is actually vertical, then the whole segment is in the convex hull, okay? But if the 2 points are not done in that way, then it's not possible. So the classical example that people give, which goes back to Tartar, so let me get this right. Okay, so an example like this. So take these 4 yellow points. Okay, then it's pretty clear that any segment which is joining 2 of these points, right, is neither horizontal nor vertical. Nonetheless, what I claim is that this square over here is inside the lambda convex hull if you define this lambda convex hull correctly. And the reason is the following. So say that you start with this point over here, right? So this point, you can write it as a convex combination of this yellow guy and... You stand on the other side. Sorry? Oh, sorry. Yes. So this point over here, you can write it as a convex combination of this yellow and this green, right? And this line is now vertical, so it's in your set of directions which is allowed. Of course, this means if you're going to write this point as a barycentric combination, you might use 1/2 of this point and 1/2 of that. Okay? Now, of course, this guy is not in the set of 4 points that you start with. But you see that you can iterate the procedure, because now you can write this point as a convex combination of the blue point and this other point which is in your starting set. Okay, so of course, if you started with putting 1/2 of the weight here and 1/2 of the weight here, now this 1/2 of the weight you can put 1/4 in here and 1/4 in there. Okay, and then you see that you can iterate. And by this iteration procedure, essentially you can write this point as an infinite series, right, of convex combinations along directions which are admissible. Okay. So and if you define the notion of convex hull correctly somehow, this means this white point is going to be there as like this point, and this point over there. And then once you have these 4 points, of course, you can draw simply the square in the usual way. Okay. And if you actually go back and look at the construction that we had, right, in which we were starting from some sub-solution and we were adding waves, right, getting to a solution. in any case, we were never getting directly to the solution. So the fact that we are doing this infinitely many times is no big deal, because we can stop our decomposition at a certain point where actually most of the weights will be on the yellow guys that we want, and then there will be some little remainder, which is a little mistake, which is not there. Okay? But after all, our construction along the iteration always allows for a sufficiently small mistake. Okay, so this actually I should have done last time. So now let me start with the talk today. So let me start with folding papers. Okay, so a classical problem in differential geometry, and this is the classical problem that made, I think, Nash very famous, as the so-called isometric embedding problem. And so we are imagining that we have a Riemannian manifold sigma G, which is smooth, and we are looking at maps U from sigma into a Euclidean space, which are immersions or maybe embeddings, and which pull back the standard Euclidean metric to your metric G. Okay? So this is one way of saying it, and if you're using this definition, then you need U to be a C1 map. Okay, and if you add in coordinates this U pullback of the Euclidean metric through U equal to G somehow in coordinate, if you write down G in components, so this is going to be the following system of partial differential equations. Right. So here, the dot means simply the classical Euclidean scalar product between the directional derivative in I of U and the directional derivative in xj of U. Okay. So on the other hand, another way you can actually define an isometric embedding is simply to say that you have an intrinsic definition of length in sigma, and you just want that curves of a certain length in sigma get mapped into curves of the same length in Rn. Okay? So it's equivalent to require that the length in the Euclidean metric of any curve U composed gamma is equal to the length in the metric G of gamma. Well, equivalent apart from the fact that this equivalence needs the differentiability, so needs actually the continuity of the differential, but in fact you can define this notion as a kind of weak notion of being an isometric embedding, even if your map is not differentiable. So if your map is, for instance, Lipschitz, that is perfectly okay. So, and we all do that, right? So I mean, this is a Riemannian manifold, a Riemannian surface, and I mean, as long as we are not tearing them apart, as long as we are not breaking, actually that's going to be an isometric embedding in the three-dimensional space, and if we want to put it in the pocket, we might do simply something like this, right? So this map has a discontinuity of the gradient, so it's Lipschitz. On the other hand, if you have a curve somehow on your paper, the length in R3 of the image of this curve is exactly the length of the curve, okay? So, and of course, everybody would just do this for like folding the paper and putting it in the pocket. Okay, so now interesting enough, one way of explaining the first theorem of Nash on this problem, actually not exactly in the form it was proved by Nash, but let's say in the form that Nash left as an exercise to the reader in his paper. So actually, Kuiper really proved the form that I'm going to tell you. So this in the 50s. So one way of stating this theorem is just to say that you don't need to fold the paper to put it in the pocket. Okay? So, or in other words, one way you could state the theorem, so maybe a little bit more serious statement. So give me any compact two-dimensional orientable Riemannian manifold.
Nash's theorem for the same n. It's the same
You don't need to fold the paper to put it in the pocket. So now I'm just thinking that the surface is 2-dimensional and your pocket is 3-dimensional. Okay, so of course one way actually so another way to state it would be actually, maybe let us state somehow the n-dimensional version. So if you have sigma g, which is n-dimensional, and if there are no topological obstructions, you can find an isometric embedding U from sigma into Rn plus 1, so in 1 dimension more. So isometric embeddings in an arbitrarily small ball. Okay. And in fact, there's a slightly more precise statement in which you will see the analogy to what I was explaining actually 2 days ago in the first lecture. So let us play the same game that we actually played 2 days ago, and let us just ask ourselves, if I give you a sequence of isometric embeddings, okay, what might happen actually to the limit of this sequence eventually? Okay, so one thing that you can actually immediately check is that this condition over here for a sequence of isometric embeddings, it's telling you that the isometric embedding is a 1 Lipschitz map, right? So you have actually a uniform Lipschitz bound, which means up to subsequence you're actually converging uniformly. So up to subsequence you're converging uniformly, but when you have actually a sequence of curves which are converging uniformly, the length might actually drop down, okay? So if you take a sequence of isometric embeddings, a natural thing to deduce on the possible limit is that the possible limit is maybe not preserving the length of the curve, but is certainly not increasing the length of any curve. I mean, it's probably shortening, okay? And this is, of course, I mean, simple to draw examples. I mean, if you have, for instance, a straight line over here and you are in 3D, you can actually wind a much longer line around it. And if you make your winding faster and faster, but the distance smaller and smaller, you actually find that the sequence of curves, which is converging to this straight curve, is losing the length in the limit. Okay? So this is just a remark. If UK is a sequence of isometric immersions converging uniformly to some u, then what is actually happening is that u is a short map. And a short map means instead of having the condition that it is length preserving, you have an inequality over here. Okay, so the definition would be u short if and only if you have the inequality instead of the equality for every curve gamma. Curve with finite length, rectifiable C1, it's actually not so important, it's just technical. Okay, and if you actually have a final map which is smooth and you want to check in terms of differential condition what this shortness is, it is actually simply the fact that if you consider this quadratic form is less or equal than that quadratic form. So short, let me maybe write it here, and C1, so short is equivalent to the inequality in the sense of quadratic form that G is bigger or equal than the pullback of the Euclidean metric. Okay? Which means if you take this matrix and that matrix, this matrix is, or that matrix minus this matrix is positive semi-definite. Okay. So you start seeing something which is very similar to what we did actually 2 days ago with the Iconal equation, right? So we were a sequence of solutions of the Iconal equation, and we converged in general, we were converging to a kind of relaxed problem. And the relaxed problem, instead of having an identity, had an inequality. And now here you see exactly the same thing. And the actual statement of Nash and Kuiper here is exactly the corresponding of the statement that we had 2 days ago for the Iconal equation. So for any short map, so for any subsolution, you can actually find a sequence of isometric embeddings which is approximating it. If you stick to C1 isometric embeddings. Okay, and how actually did Nash prove this theorem, and how also Kuiper, because Kuiper's proof is just a modification of Nash's theorem. So Nash actually gave the details for m plus 2 instead of m plus 1. So in his paper, he's proving this theorem where here there is m plus 2. And then he's saying that it's doable in n plus 1, but the computations are more complicated. So Kuiper does it in n plus 1. So let me give you a kind of sketch of a proof. So it will be very, very sketchy. But, I mean, given what I've explained 2 days ago, you will see somehow a very similar philosophy. So what I want to do is I want to implement an iteration which is starting from a short map, and is actually, at the end of the iteration, giving you the isometric embedding. So I can actually measure the distance of the short map to be an isometric embedding by looking at what is the error that I make when I subtract to G the pullback metric. Okay? And with the idea that we're going to do an iteration, the only thing that I have to understand is when you give me a short map, which is strictly below G, how do I actually improve it? So how do I add a perturbation so to make this short map much closer to be an isometry, but staying close to it in C0? Okay, so the essential problem is to start with U short, and let me actually put strictly short. So let me just assume that G minus U sharp E is strictly bigger than 0, and improve it to a U tilde, which is close uniformly to U and less short. Okay, so let me give you the basic idea. So first of all, what I'm going to do is the following. So G minus U sharp E, if you want, I'm, after all, just a bloody analyst. So I will think about this as, in coordinates, as this symmetric matrix. Okay? Now, if I have a symmetric matrix, I can always decompose this symmetric matrix in rank 1 matrix. And I can actually decompose in rank 1 matrices which are positive semi-definite. So I can write this as a linear combination of something which looks like this: a squared I vi tensor vi. Maybe let me use L. Okay? So and now what I want to understand is how I can actually perturb the map U to a new map U tilde, in which instead of having this summation, you have kind of the summation from L equal 2 to N. And a much smaller error. And in codimension 2, of course, while U tilde staying very close to U. And in codimension 2, the answer is surprisingly easy. I mean, I can actually just give you the explicit construction, which is what Nash does. So you define U tilde x to be Ux. And then here I'm going to have a1 of x. Then I'm dividing by lambda. I'm having nx. And here I'm taking cosinus of lambda v1 dot x. And here I will have a1x divided by lambda, and here I put the binormal times the sine of lambda v1 dot x. Okay, and what are n and b? Well, Nash does things in codimension too. So if you think of u of sigma as a submanifold in Rn plus 2, n and b are just two, I mean, you're just a base for the normal bundle, an orthonormal base for the normal bundle. So what I want is that n has modulus 1, like b, n is orthogonal to b, and n and b are both orthogonal to the tangent space to v of sigma, to u of sigma. Okay? And you will notice the following interesting fact. So I will shoot, so you remember this lambda we had also in the construction of 2 days ago. So we'll actually shoot this lambda very high, very, very large. So when I compute the derivative over here of the u tilde of x, I have du of x, and then I have two portions. I mean, I have when I am differentiating the cosine, and the lambda is getting out to cancel with this lambda, and when I'm differentiating the rest. And when I'm differentiating the rest, I will have this 1 over lambda in front. And if I'm thinking that I will choose 1 over lambda very big, essentially I can kind of ignore it. Okay? So I will have then the following. I will have a1 of x, then I have n of x tensor v1, and then I have the cosine. No, I have minus the sign because I have to differentiate. Okay, then I will have a1, I will have b tensor, again, v1, and then I will have the cosine. Okay? And then I have all bunch of errors when I am differentiating a1, b, n. Okay? Yes, and all of this, I will just treat them as a big O of 1 over lambda. And now what happens? It happens actually that since you have the orthogonality conditions between n and b, right? When I'm going to compute the metric, okay, the metric, which is a quadratic expression in u tilde, actually will essentially be the sum of the quadratic expression on this, the quadratic expression on that, and the quadratic expression on that. And the reason is simply in these simple orthogonality conditions. So if I carry on my computations, which is not too difficult, you will see immediately that when I compute the metric, so the metric is actually du transpose times du transpose tilde. This is du transpose times du. Then there's going to be a squared v1 tensor v1 sine squared, and then there's going to be a squared v1 tensor v1 cos squared. So this is what is coming from these three separate parts. And then, of course, there will be the error, which is messing things up, because this error will have non-trivial interaction with these other terms. And, of course, it will have also a non-trivial interaction with itself. But everything which is remaining as big O of 1 over lambda. And, of course, now what you see over here is that the sine and cosine were actually chosen because the sum of them squared is equal to 1. Okay, so these ones, you sum them, and then you got exactly what you wanted, which is the pullback of E, the metric that you wanted to add, and then the small error. Now, if you iterate this a finite number of times, you essentially land with a new map, which I'm not going to call u tilde. I mean, it will need it somehow n times of this construction, but essentially you have reached with the new u tilde almost your metric G, and then you have done a small error. And this small error, actually, you can make it much, much smaller than what you started with. And the reason why you can make it much, much smaller is because this lambda is to you to choose. So you can choose it huge, and then that will become very, very small.
Can you comment on the loss of derivatives? I mean, I know later somebody gave a proof to that loss of derivatives for this problem. So when you carry this out and keep track of the function spaces.
Yeah. So now, of course, what is happening is that if I'm computing a second derivative over here, right, there will be 2 times lambda coming out. And since I'm shooting lambda actually to a very high, very high frequency, so the second derivative actually will blow up.
So he had to
right.
use Newton.
Right. Yes, but that is. So somebody later, I think you're thinking about Günther.
Yeah.
Okay, so Günther actually finds, okay, so this, of course, I mean, you're talking about the hard implicit function theorem part. Okay, so when you're doing the hard implicit function theorem, you will never have the chance of doing this in codimension 1. You will need a much higher dimension. So now you see that in this method, what is actually quite surprising is the following fact. You see, instead of linearizing the equation, I'm quadratizing the equation. Okay, now it means the following. So if you look at this, I mean, if you look at this big O of 1 over lambda, so there is an interaction between this guy and that guy, right? When you compute the metric, right? And this big O of 1 over lambda. So I'm actually making the linear part much smaller than the quadratic part, and then I don't have any chance of getting something too smooth. Okay. So what actually happens is that in higher dimension, when you get sufficiently close to the to being a metric, instead of keeping going on this quadratic sort of method, you try to linearize. Okay, now if you try to linearize, you have that phenomenon which actually implies the loss of derivative. So now what Günther discovered in the 80s is that if you make the right kind of ansatz, in a sense, on how you want to solve the linear equation, you actually get a classical elliptic PDE. And once you get a classical elliptic PDE, you don't have to worry anymore about the loss of derivative, because you will just have a classical Banach fixed point argument, for instance, to find the solution to the linearization. Right. But to explain that, one would have to go through kind of some detailed computations, actually, on the linear problem. Okay, so anyway, so this was very useful because I already told you there is no chance that this method is kind of converging with too many derivatives, right? So because when we start computing higher derivatives, I will start having somehow powers of lambda which are coming in front, and this method actually requires at each step to take lambda quite large, okay? So the second derivatives will typically explode. Okay, on the other hand, in fact, we know that the second derivatives have to explode because, for instance, you can prove the following classical theorem. So if, say, I give you a manifold sigma g, which is actually the standard sphere with a metric of positive curvature, any C2 isometric embedding, even immersion, but let us stick with embedding, gives a convex set, isometric embedding in R3. So gives a convex set means the image of S2 through your map. So let me call U the map. So U of sigma is the boundary of a convex body. Now, of course, you can compute the area of the boundary of this convex body. And the area is given by the metric. So in particular, if the metric is large, the area of the boundary of the convex body is large. There is no chance that you're going to put it in your pocket. Okay? I mean, if it is a sphere like this big, it's not going into your pocket. You can, of course, try to squeeze it in some directions, which is what you can do, but you will not be able to squeeze it in all directions. So you see something interesting. There is a rigidity theorem in C2, and there is a flexibility theorem in C1, which at the time was extremely surprising. In fact, differential geometers of the time thought actually that this theorem should hold in C1, and also it was a technical problem to prove it. So Nash proof came as a surprise actually on disproving that. Okay, so let me give you a small sketch of this. So how would you prove something like that? Well, surprisingly simple. So the key idea is the following. So the key idea is the following. So say that your set is not convex, something like this. Okay? And look at something like, for instance, the height function in here. Okay, so with the height function, you see that the non-convexity is giving me two critical points, right? Over here, which are local maxima. So here there will be a local minimum. But then here there is a saddle point. So in fact, it's a simple exercise. It's Morse theory is that if you have two local maxima, you will have at least one saddle point.
Just really working in Morse.
Right. So now, what happens? Now, what happens at the saddle point? Well, you see immediately that actually this is, I mean, if you want this saddle points, what it corresponds to a point where the differential of the Gauss map cannot be positive definite. But if the differential of the Gauss map cannot be positive definite, then the determinant of the differential of the Gauss map has to be negative. But if the determinant of the differential of the Gauss map is negative, then the curvature cannot be positive because you're applying Gauss theorem. So that tells you something interesting besides that for a C1 isometric embedding, Gauss theorem fails. Now you could say, well, it's no surprise because, I mean, if you have your isometric embedding which is only C1, you cannot compute the determinant of the Gauss map. But it's not completely true because what you can certainly compute, I mean, if your map is C1, your normal is C0. And if your normal is C0, I can certainly look at images of sets. So you give me a set, I can look at the image of that set. And you could actually state a Gauss theorem by saying that the area of the image of the set should be computed by integrating the Gauss curvature. Okay? Well, this is actually going to be wrong if you have a C1 embedding. But that's an interesting fact. So Borisov in the 50s actually proved that Gauss theorem is essentially valid if you don't have two derivatives, but you have one derivative and enough Euler regularity for the one derivative. So by this I mean that my immersion is going to have the following control on the modulus of continuity of the derivative. So I'm not saying it's only C1, I'm saying it's actually slightly better. So, and this is just to say that although you cannot compute the determinant of the Gauss map, if you give the correct meaning to Gauss theorem, you can still prove it when you are sufficiently high in the Euler regularity. And Borisov in the 60s also showed that in C1 alpha for alpha sufficiently small, the Nash-Kuiper theorem is still valid. The Nash-Kuiper theorem is still valid. And in particular, the Gauss theorem fails. In fact, for 2D surfaces, the best exponents that we have so far is in a paper by myself, a student, and Laszlo. And this exponent alpha, you can make it as close to 1 over 5 as you want. So alpha has to be simply less than 1 over 5. No. Okay, so what actually Gromov considers the correct exponent, and apparently also Borisov, as far as I got. But okay, so Borisov died actually before I could talk to him, or Laszlo could talk to him. So the conjectured exponent is 1/2. And that is what is called that is what I started calling Borisov-Gromov problem. There is some reason. Yes, let me actually give you for instance, one first intuitive reason. Yes. So Gromov conjectures that it's independent of dimension. But the rigidity theorem is only actually proved for 2/3. Why, actually? So there is an equivalent of this Gauss theorem is still valid in C1 2/3 plus epsilon in any dimension. But then to conclude the rigidity theorem, you're using Pogorelov's theory of convex bodies in R3. And that does not exist in higher dimension. So you could say that's a little of a technical problem. Here, the exponent becomes worse and worse as you go to higher dimensional manifolds and when you introduce topology, actually. So it's a pretty, in the proof, that in the best proofs that we have, this alpha is computable and it goes down like 1 over n, essentially, right? So it's like 1 over 2n plus 1 or something. Okay, so something computable. It's not too bad, but it's going to 0 as the dimension goes to infinity. Okay, so a reason for this 1/2. Yes? Let me give you, for instance, one reason. And this is a reason remark by, a reason theorem by Olbermann and Züst. So I told you when I look at the Gauss map on a set omega, right? What I can actually take into account is I apply the Gauss map on the set omega, right? I look at its image, okay? And then when I look at its image, I can compute the area of the image. And that is described by the integral of the Gauss curvature, right? Not quite. Because actually the Gauss map can come back and forth, right? And if you integrate the Gauss curvature, sometimes you will have positive terms and sometimes you will have negative terms. So there are some cancellations. Okay? So if you actually work out what you should do, you should write down the change of variable formulas correctly, which means that you should count positive orientation and negative orientation. Now, when you're counting positive orientation and negative orientation, you're counting actually the Brouwer degree, essentially. Okay? So for the Gauss map, you could write something like the integral over omega of the Brouwer degree of your n with respect to your set omega, y dy. Sorry, this is the integral over S2. This is equal to the integral over omega of the Gauss curvature. This is the correct formula, where I'm taking into account possible cancellations. Okay, this function is a very well-defined locally constant function by Brouwer theory. Now, what is funny is if omega is a nice set and in two-dimensional, and this n, which is the Gauss map, so it's kind of the derivative of the function, is C0 1/2 plus something, then the Brouwer degree is actually in L1, which means I can actually make sense of this integral. Otherwise, it's not. Below, it's not. You can actually draw counterexamples. So that might actually give you an indication why that might be a borderline situation. So it's, for instance, the only situation in which I can write my extra identity, in which I can actually state the change of variable formula, or if you want, a weak form of Gauss theorem. And there's a funny remark. So this is actually, I think it's fairly interesting somehow. So depending on the Hölder exponent, you have not only L1, but as you increase the exponent, you have a certain LP. Well, in fact, so this is something I worked out with my student. There is an optimal Sobolev regularity when you're varying this C alpha from 1/2 to 1. And actually, in n dimension, when you are varying from n minus 1 divided by n to 1. So the Brouwer degree is, in fact, in some fractional Sobolev space. And the theorem of Olbermann, for instance, which gives you a certain LP estimate, is a consequence of this if you just use Sobolev embedding.
You know this conjecture resists for just the Cauchy formula of the degree of a map. I mean the smoothness of a map for which Cauchy
No.
There's a 1/3 there also.
No, I'm not.
Man-made counterexamples.
I'm actually not even aware of the problem, so that's a good suggestion. So I should look into it. Right. Because unfortunately now we have these nice theorems, but we cannot do anything in improving this exponent from 2/3 to 1/2. So I was very excited when I saw this. So now we have these nice estimates, but we don't know what to do with them. I mean, we know that we can write down, for instance, the identity that we would like to prove, which is already a step, right? Because if you cannot write it down, it's a pretty bad sign. But on the other hand, I cannot use it for anything. Okay, so now let me go back to the Euler equations. By the way, here there are several works that I would have to cite, but then I would have to lose time somehow. So from the time of Borisov, now we have much better proofs of these results. I mean, these were quite long and technical proofs, which had also some suboptimal assumptions, and now we can clean this up, and it's again a joint work with Laszlo and Sergio Conti some time ago somehow. Okay, so now you see some interesting analogy between the Euler equations and the isometric embedding problem. So what I told you last time is that if you have L infinity solution, you might have solutions which do not conserve the energy. Okay, for the isometric embedding, what you actually know is that Lipschitz solution do not respect Gauss theorem, right? That's kind of pretty obvious. Because when I'm folding the paper, I'm actually introducing a curvature which is very singular in there. Whereas if I have a nice surface, for instance, if I have a flat surface, the curvature is identically equal to 0. Okay? Now, what Nash is telling you is that even C1 solution might not respect Gauss theorem. And in fact, what Borisov is telling you is that even C1 alpha solutions might not. And then there is some borderline, some threshold, and at a certain point you will start actually still agreeing with Gauss theorem, and that is actually Borisov. And there is a land of nobody in between when we don't know what happens. Okay, now for the Euler equations, actually a situation like this was predicted by a physicist in 1949. And this is what goes under the name of Onsager's conjecture. So there is something similar, and there is a very precise threshold. And the very precise threshold is 1/3. And the Onsager conjecture is telling you for C 0 alpha, alpha below 1/3, there is energy conservation. So here I'm going the other way around, right? So alpha bigger than 1/3, no energy conservation. And for alpha less than 1/3, there is energy conservation. Eh? The other way around. So yes, okay, actually I was doing it correctly at the first time, sorry. Right, so the threshold is 1/3. And it's absolutely surprising that actually he came out with this conjecture almost 70 years ago. Now, to tell you the truth, I'm cheating you quite a lot. So I've shown you that kind of these constructions in the theory of differential inclusions are very similar to what Nash did in the 50s. But actually people didn't realize that until 1999, when Müller and Sperak actually drew the connection between what people were doing in the theory of differential inclusions and what the geometers had been doing by following up Nash through the work of Gromov and so on, since these constructions were used in several other places. And they drew the connection between the two of them, but of course, in the literature of differential inclusions, you work with Lipschitz maps. In convex integration, or somehow in the theory of Gromov, you work with differentiable maps, with C1 maps. So there is a mismatch between the two. So of course, when we proved our theorem on Euler, we knew that there was this connection. We didn't know of the Onsager conjecture, but a good friend of us told us, oh, the interesting part is actually that one. And then we noticed that in the literature, there were these results by Borisov, which were strikingly similar. So we started wondering whether actually this could be an approach to prove that. Anyway, the positive part of the Onsager conjecture, so alpha bigger than 1/3. So this was proved by Konstantin A. and Titi in 1993 or 1994.
I'm curious, from your last lecture, you managed to state this without saying the word weak solution, which I liked, because I doubt Onsager used those words.
Yeah.
So is there a formulation, the way you spoke in the first lecture, you were giving these sub-solutions, and you stated in that language.
Right.
And that can be done, you can avoid the language of weak solutions in stating Onsager?
No, I mean, of course, you have to say what is your concept of solution. So the way he does it is he uses Fourier series. Right. And you can do the way we do. I mean, you can really think of a matrix which is divergence-free and which is taking values in that algebraic variety. So the two things are actually perfectly equivalent. Of course, I mean, I'm not using the word weak solution, but of course, what I was defining is essentially a weak solution. Right. And in these things which I told you, for instance, in the modern proof of Borisov rigidity theorem, we are taking advantage of an estimate which has been invented here somehow. So there is a striking similarity even from the point of view of the rigidity. Anyway, when, of course, we saw this connection, we thought maybe the Onsager conjecture can actually be approached in this way. And in fact, it turns out that the Onsager conjecture can be solved in this way. So Laszlo and myself in 2012 actually could, after quite some time that we were thinking about it, we could upgrade our construction from bounded solution to continuous, right? I mean, it's pretty clear that you actually have to go through a barrier because there is a substantial difference between the L infinity construction and the C0 construction. You see it already in the isometric embedding theorem. I mean, it's absolutely not surprising that you can actually fold the paper and put it in your pocket, but that you can do it C1, this was somehow astonishing the differential geometers of the time. So now there's actually even a bigger step in the case of Euler because already the L infinity construction is much more difficult than getting somehow Lipschitz solutions of the isometric embedding problem. So we could do C0. Okay, and immediately after, since we had the previous experience with the isometric embedding problem, of course, we knew that we could do some Hölder exponent. And the first surprising thing that we encountered is that maybe because we were pessimistic, but we were expecting we get an exponent which is completely meaningless. I mean, something which is very small, I don't know, maybe a million, maybe an epsilon, which is not even quantifiable. But even the first exponent that you can get by very brutal argument is kind of essentially the order of magnitude of the threshold, this 1/10. Okay, and then this is here when Phil Ez actually came into the game and started introducing very interesting ideas. So he could improve it to C0 1/5. He had a pretty long proof of this. So together with Tristan Buckmaster, we had a simple proof and with some extra feature, which I will tell you in a moment. And then again with Tristan, actually, we could prove, I think in 2014, what we call L1 in time and C0 1/3 minus in space. Okay, so what does this mean? Actually, if you look at the conjecture of Onsager, he's not claiming any Hölder constant in time. Okay, so his Hölder constant is only, his Hölder regularity is only in space. And the way he's stating the conjecture is the following. Right, so this will mean this constant is uniformly controlled also in time, and then it gives you the Hölder regularity in space. So what we are doing over here with L1, it means that this constant is actually allowed to vary in space, but then its integral is finite. So you have a C, you have a constant which depends on t, and this quantity is finite. Okay, and finally, Phil could actually prove the conjecture just a few months ago. And of course, this reached what we were dreaming actually several years ago. I have to say, though, there is some development which is very important. So he's using an idea which appeared in a recent paper by Sara Daneri and Laszlo, which is fundamental. So somehow he's introducing one new idea with respect to the previous construction, but he's using also one idea from here, which is fundamental. Okay, now a little bit more on the technical level. Actually, if you look at the way Onsager states the conjecture, he's not talking about the fact that solutions do not preserve the energy. He's really talking about solutions which dissipate the energy. So if you want to be really picky, actually, this would be a more precise theorem. And in fact, that can be also proved. So, and this we just did together with Tristan and Vlad Bikol. I mean, it's a nice addition, but of course you have to say that it's still using substantially the main ideas that he has introduced here. Usually when you actually are able to handle dissipative solutions, it comes with an added bonus. In our experience, you actually get a cleaner proof. I mean, you have a more difficult statement to prove, and then you get a cleaner proof somehow. So this, for instance, our proof is substantially shorter. Okay, so now this is just...
So more precisely, what do you mean by a dissipative solution?
Energy is going down. Decreasing energy.
It's not going down to zero?
And keeps going down, you could even just get it to zero, right? I mean, actually, we don't do that. It might be technically a little bit more difficult, but yeah, it could go down to zero. Actually, what is showing is that there are compactly supported non-trivial solutions because you cannot keep track of the energy. So to say that it's not conservative, it actually shows that the energy is zero somewhere and it's positive somewhere else. But then it doesn't keep track of the energy, and since the function is Hölder, of course, you could imagine that your energy profile looks like a Brownian motion. There will be no interval in which there is a definite monotonicity. One also has to add that the equation is time reversible, right? So if you have something which has the energy going down, of course, you have also something which has the energy going up. So it just needs to have a sign on the energy. Okay. Actually, our theorem is a little bit more precise. So there is a statement like the one I told you, for instance, 2 days ago, that is the best statement or the worst statement. It depends on how you look at it. So it's something like there is a well-defined notion of relaxation of the solution. And if you give me a relaxed solution, I will be able to approximate it with solutions of the Euler equations, which are C0 1/3. Okay, and these solutions, I mean, intrinsic in this kind of relaxation formulation, there is a control, an explicit control of the energy. So in particular, you can fix kind of the energy profile in the way it is defined. But it's nice because we always argued that this seems to be very similar to this H principle. So what is ultimately the H principle? For instance, in Nash theorem, the H principle is if you give me a short map. So if you give me a solution of the relaxed problem, I can actually approximate it with an exact solution. And this theorem comes with something similar. So this was also the focus of this paper by Sara Daneri and Laszlo Székely-Hidi, where they didn't have yet the optimal exponent, of course. So there is an ultimate theorem which is telling you there is a precise notion of relaxed solution, which I'm not going to give you because it requires some time. And you can actually approximate any relaxed solution with exact solutions as long as you are in this C0 1/3 minus epsilon. Okay. And so with this, let me finish my lecture. So what am I going to do actually in the third one? Well, okay, so in the third one, I want to give you a glimpse on how you do this. And of course, I will not be able to really give you the idea why, for instance, you get stuck at certain exponents. I mean, this 1 over 5, I mean, is an exponent which has a certain meaning. This 1 over 10 is completely fake. Already, like, one day after we saw this 1 over 10, we realized we could improve the exponent, actually. So this was just to get the first ever exponent, and who cares. But this 1 over 5, for instance, was an exponent with a certain precise meaning. I mean, there was a certain abstraction. I will not be able to go into the details of this, but what I will try to do is I will try to give you an idea on how you actually can produce continuous solutions. And also, I will give you a back-of-the-envelope computation in which you will see this 1 over 3 as a clear kind of threshold which you see very naturally if you approach things in a certain way. Now, it will be kind of tailored on the Euler equations, but then on the other hand, actually this mechanism that that we are describing, so that we started this, that we introduced back in 2012, can be used, can be stretched in a lot of other situations. And in fact, people have used it in other situations. So, for instance, they have been used by Filizet and Vlad Vikol for active scalar equations. They have actually, now it has been used by Tristan, Scholler, and Vlad again for SQG with some dissipation inside. So, I mean, it actually is more flexible and more general than it looks at the beginning. I mean, there is some generality in this procedure that actually opens up similar questions in a lot of other situations. Thank you.